The letter Z is often used to denote a complex number. So here we have the complex number Z plus 3i. I put a line through this Z to avoid confusion with the number 2. If Z equals 2 plus 3i, then the complex conjugate of Z is denoted by Z with a bar on top of it. It's 2 minus 3i, so you can see what you do. We just take the sign of the imaginary part. The imaginary part of Z is plus 3, and we change that sign to its opposite. So plus 3 becomes minus 3. Let's look at what happens when we multiply Z by its complex conjugate, Z bar. So we want to take 2 plus 3i and multiply it by its complex conjugate, 2 minus 3i. So as you saw in the previous video, we just do this like ordinary multiplication in algebra. We take this term here and multiply it right through the second brackets. So we get 2 times 2 is 4. 2 times minus 3i is minus 6i. Then we go to the next term, plus 3i, and we multiply it through. So we'll end up with 4 terms in total. Plus 3i by 2 is plus 6i. Plus 3i by minus 3i is minus 9i squared, because we've I times I here. Now, we know of course that I squared is minus 1. So the only difference between here and ordinary algebra is that we have to replace this I squared with minus 1. So we have minus 9 times minus 1. Well, that just gives us plus 9. So basically what happens is, if we have a number times I squared, we just end up changing the sign of that number. So here we get plus 9. Now if we get our like terms, we've plus 4 plus 9, that's plus 13. But look at the imaginary terms. We've minus 6i plus 6i, that gives us 0i, or just 0. So I can leave that out, but well, if we leave it like this, we have the complex number 13 plus 0i. This complex number is the real number 13. So when we multiply 2 plus 3i by its conjugate, we get a real number. In other words, we get 0i. That always happens. If we take any complex number and multiply it by its conjugate, we get a real number. More generally, if z equals x plus yi, where x and y are any real numbers, then we know that z bar is going to be x minus yi. We just change the sign of the real part. And if we take z and multiply by z bar, now you don't need to do this thing here, but I'm just doing it as an aside. It's basically multiplying x by x to give x squared. X times minus yi gives minus xyi. Yi times x gives plus yxi, or yix, it doesn't matter which way you write it. Yi times minus yi, plus by minus gives a minus, but we have y times y giving y squared, and we have I times I giving I squared. Now these two terms in the middle cancel out. That always happens. These are like terms. Minus xy is opposite in sign to plus xy, so that gives us 0. And we get x squared minus y squared times I squared, but we know that I squared is minus 1. So what we get is x squared plus y squared. So this is the general form. You don't really need to do this thing, what I've just done here. It's really just an aside. Basically, if you multiply a complex number by its conjugate, we get the sum of the squares of the real and imaginary parts of the complex number. So for example here, we get the sum of the squares of the real and imaginary parts. 13 is just 2 squared plus 3 squared. X is 2, y is 3. Now let's look at the division of complex numbers. So I want to start with this example. We have the complex number 3 plus 4i divided by the complex number 5. Well, the complex number 5 is actually a real number because its imaginary part is 0. But when we do this division here, it's quite easy. We just have a single term underneath the line, so we can just write this single fraction as two fractions, 3/5 plus 4/5 I. So we've taken two complex numbers, 3 plus 4i and 5 plus 0i, and written them as a single complex number, whose real part is 3/5 and whose imaginary part is 4/5. Now that was easy because we just had a real number in the denominator. We can just break it down into two parts like this. Now suppose we have the complex number 3 plus 4i over or divided by the complex number 2 plus 5i. How do we make sense of something like this? Well, what we want to do actually is to write these two complex numbers as a single complex number. So you'd often see a question like this: write 3 plus 4i over 2 plus 5i in the form x plus yi. Basically, all this means is we want to write this complex number as a single complex number. This is a single complex number, so we have to find out what x and y are. Now the way we do that is make use of the idea of complex conjugate. So we want to take 3 plus 4i over 2 plus 5i and change its form so it appears as a single complex number. The way we do that is we multiply above and below by the conjugate of the denominator. The denominator is what's downstairs. So the conjugate of 2 plus 5i is 2 minus 5i. We just change the sign of the imaginary part. So we change from plus 5 to minus 5. But of course, with any fraction, if you multiply underneath by a certain amount, certain quantity, you must do the same multiplication on top. Like if you take any fraction, say 3 over 2, and you want to multiply underneath by, say, 5, then you must multiply on top by 5. So the ideas for multiplying ordinary fractions extend for working with fractions that have complex numbers in them. And multiplying these two fractions is just like multiplying two fractions that are real numbers. You know, we multiply the numerators together and we multiply the denominators together. Now, I'll multiply the numerators together. So that's, you can put these in brackets if you like. So we take the 3 and multiply it into all of this. So this is just multiplication, which you've seen in the previous video. Multiply 3 into this here. 3 2s are 6. 3 times minus 5i is minus 15i. Then we take the plus 4i and multiply it into this. So 4i by 2 is plus 8i. Plus 4i by minus 5i is minus 20i squared. We can simplify that numerator. We know that I squared is minus 1, so we replace this with minus 1. So this term at the end will become plus 20. Basically, this number changes sign. We have minus 20 by minus 1 giving us plus 20. We can then gather the 6 and the 20 together. 6 plus 20 gives us 26. And minus 15i plus 8i gives us minus 7i. Now we multiply the denominators together. This is just like multiplication of ordinary fractions. If you say you want to multiply 3/4 by 5 over 5, just 3 by 5 over 4 by 5, same idea. So we multiply this 2 into this here. So we have 2 times 2 is 4. 2 times minus 5i is minus 10i. Now we go to the next term, which is plus 5i. We multiply plus 5i by 2. That gives us plus 10i. And then we've plus 5i by minus 5i is minus 25i squared. Of course, this here will become plus 25 because I squared is minus 1. Now, as I explained to you earlier, when we multiply a complex number by its conjugate, we get a real number. The I terms cancel out. We get minus 10i plus 10i gives us 0i or 0. So what we get in the denominator is a real number. 4 plus 25 is 29. So as you saw earlier, we can write this as 26 over 29. This is just writing a single fraction as two fractions. When you just have a single term, we can conveniently write it like this. And this is our answer. We have written 3 plus 4i, the complex number 3 plus 4i divided by the complex number 2 plus 5i in the form x plus yi. In other words, as a single complex number. This is just one complex number. Its real part is 26 over 29. Its imaginary part is minus 7 over 29. So just to remind you what you do, when we have a fraction like this, we look at the denominator, which is 2 plus 5i, and we multiply above and below by the conjugate of that denominator, which is 2 minus 5i. So we multiply above and below by the conjugate of the denominator. If you want to check your answer, you can go to wolframalpha.com or other websites and show your division like this. Put 3 plus 4i in brackets, and you want to divide it by 2 plus 5i. The letter I here is understood to be the square root of minus 1. So Wolfram Alpha understands I to be what we want, which is the square root of minus 1. And here's the result. So we've written these two complex numbers as a single complex number. 26 over 29 minus 7 over 29i.